Hello friends. Welcome to my channel. Alright everyone, as you can see on the screen right now, we have a curated list of 10 essential Swift interview questions. If you are a junior developer, or if you have around 1 to 2 years of experience as an iOS engineer, these are exactly the kind of foundational and conceptual questions tech leads love to throw at you. They don't just test if you can write code, they test if you actually understand how Swift works under the hood. We're going to deep dive into each of these slide by slide. We'll cover everything from memory mechanics to execution states, showing you exactly how to answer like a pro. Let's jump straight into question number 1. So, starting with question number 1, what is Swift? If an interviewer asks you this, don't just say, it's a language for making iOS apps. You want to give a comprehensive, structured answer. First, hit them with the core definition. Swift is a multi-paradigm, compiled programming language built by Apple for their entire ecosystem, iOS, macOS, tvOS, and watchOS. Because it's compiled using the open-source LLVM compiler, it runs incredibly fast. It's also versatile. While we mostly use it for front-end app development, you can absolutely use it for back-end server functionalities too. One of its biggest strengths is interoperability. Swift runs on the Objective-C runtime library. This is a massive deal because it means you can seamlessly mix Swift, C, Objective-C, and C++ code within the exact project without rewriting legacy systems. From a developer experience standpoint, it's safe, fast, and highly interactive. Apple designed it to strip away the old boilerplate clutters of Objective-C. For instance, look at its modern syntax features. We get named arguments, which essentially makes our APIs read like clear English sentences. There are no semicolons required to end statements. Modules replace old traditional header files, giving us clean namespaces. And we have inferred types, meaning the compiler handles the data types automatically, making our code much cleaner and less prone to human error. Moving on to how Swift handles things under the hood. First, let's talk about advanced string handling. Swift strings are fully Unicode correct and use UTF-8 encoding. This means it natively and highly efficiently handles international languages, special characters, and emojis out of the box without breaking character counts or memory alignment. But the real kicker that interviewers love to test you on is memory management. Swift manages memory automatically using ARC, or automatic reference counting. Unlike other languages that rely on a background garbage collector, which can pause your app and cause UI lag, Swift's ARC tracks and manages memory deterministically in real time. It increments and decrements reference counts, and the exact moment an object's reference count hits 0, that memory is freed up. This keeps the application's memory footprint incredibly low and its performance blazing fast. Answering like this shows the interviewer you don't just write the code. You understand exactly how the language optimizes performance. Moving on to question number 2. What are the key features of Swift? When an interviewer asks this, they want to see that you understand both the structural advantages of the language and its modern coding capabilities. Looking at our first set of features here. First up, Swift is completely open source and secure. Comes with robust, built-in error and exception handling mechanisms right out of the box, making your code highly predictable and resilient. Next is automatic memory management, which uses ARC, automatic reference counting. Coming from its Objective-C roots, ARC automatically tracks your class instances and destroys them in real time the exact moment they are no longer in use. This is a massive win because it completely frees us from manual memory tracking, letting developers focus on building features rather than hunting down memory leaks. We also have advanced type features. Swift heavily supports powerful generics and extensions, which allow us to write highly reusable, modular code. And a huge highlight here is how Swift handles structures. Unlike traditional languages where structs are very limited, in Swift, structures are first-class citizens. They can support methods, extensions, and conform to protocols just like a class can. Finally, Swift embraces modern functional programming. It features first-class functions and an incredibly clean, lightweight closure syntax. This makes it effortless to pass functions around, store them in variables, or pass them into data structures. Continuing with the features on our next slide, let's talk about expressive syntax and control. Swift gives us tools to write highly readable, compact code. For instance, it allows for incredibly swift, short iterations over ranges and collections, turning what used to be complex loops into single-line statements. It also supports tuples and multiple return values. This means a single function can return multiple structured pieces of data directly, without forcing you to build a custom class or struct just to pass data back. And lastly, Swift features incredibly powerful pattern matching alongside custom enum payloads. This allows you to attach actual data values to an enum case and unpack them cleanly using switch statements. Highlighting these points proves to your interviewer that you don't just write Swift, but you appreciate the modern paradigms that make it so powerful. Moving on to question number 3. What are the advantages and disadvantages of using Swift? This is a critical interview question because it tests your objective understanding of the platform's trade-offs. Let's look at the advantages first. To start, Swift is fast, type-safe and memory-safe. Its execution speed rivals C++. Type safety catches errors at compile time rather than runtime, and memory safety prevents nasty pointer crashes. This drastically shortens the debugging feedback loop. Next, mention interoperability. If a company has a massive legacy app written in Objective-C, they don't need a full rewrite. Swift integrates beautifully with Objective-C and C++ files right inside the core project. Swift also makes apps easier to maintain. Unlike Objective-C, which splits code into separate header and implementation files, Swift unifies everything into a single .swift file. For users, this efficiency translates into smaller app sizes and lower memory usage. Finally, don't forget to highlight ABI stability, which ensures binary compatibility across libraries, and optionals, which act as a safe container around variables to elegantly prevent null pointer app crashes. However, no language is perfect, and interviewers love to see that you can acknowledge the downsides. First, Swift is relatively young. It was introduced in 2014, whereas Objective-C has been around since the 1980s. While the ecosystem is huge now, you might still occasionally find fewer open-source niche libraries compared to decades-old languages. Second, binary compatibility can still be tricky. Even with ABI stability, managing complex static libraries and dependencies compiled across shifting, older versions of Swift can still trigger integration headaches. Lastly, Swift is not a fully reflective language like Java or Kotlin. It provides the mirror struct, which allows an object to inspect or self-describe its own properties at runtime, but it cannot dynamically alter its own behavior or inject dependencies from within. Structuring your answer this way proves to the interviewer that you have a mature, well-rounded perspective on the technology stack. Moving on to question number 4. How is memory management handled in Swift? This is one of the most heavily tested topics in iOS interviews, so you want to nail this explanation. The short answer is, Swift uses ARC or automatic reference counting. Conceptually, it works similarly to how it did in Objective-C. Here is exactly how you explain the mechanism to an interviewer. First, clarify that ARC only manages reference types, like class instances. It does not apply to value types like structs or enums, because those are copied when they are assigned. Next, explain the math behind it. Every time you point a variable, constant, or property to a class instance, ARC automatically increments its reference count by 1. If that variable goes out of scope, points to a different object, or is explicitly set to nil, ARC decrements the count by 1. The moment that reference count hits exactly 0, ARC instantly deallocates the memory consumed by that object in real time. Finally, make sure to mention that by default, every reference you create in Swift is a strong reference. If you don't manage these properly, you can accidentally create reference cycles, which lead to memory leaks. Answering it this way shows you completely understand the memory lifecycle under the hood. Moving on to question number 5. What is the key difference between upcasting and downcasting in Swift? This question tests your understanding of type hierarchies and type safety. The core difference comes down to compile time certainty versus runtime risk. Let's start with upcasting. Upcasting means you are moving up the class hierarchy, taking a specific derived subclass and casting it to a more generic base class. For example, treating a UI button simply as a generic UI view. Because a button is structurally a view, the compiler can verify this relationship instantly at compile time. Therefore, upcasting using the standard as keyword is completely guaranteed and will never fail at runtime. Downcasting, on the other hand, goes in the opposite direction. You are moving down the hierarchy, taking a generic base class object and trying to cast it into a specific subclass. An interviewer loves examples, so you can explain it like this. Imagine your code receives a generic UI view. At runtime, that view could actually be a UI table view, a UI button, or a UI image view. Because the precise type isn't guaranteed, downcasting can fail. To handle this safely, Swift requires us to use conditional downcasting with as, which returns nil if the cast fails, or force downcasting with as, which will crash the application if the type doesn't match perfectly. Nailing this distinction proves to the interviewer that you understand how to write safe, defensive typecasting code in your apps. Moving on to question number 6. What is the difference between the double equals operator and the triple equals operator in Swift? This is a fantastic question that tests whether you understand the difference between value equality and pointer comparison. The fundamental difference comes down to comparing what an object holds versus where it lives in memory. Let's look at the double equals operator. This checks for structural equality. It compares data values to see if they are conceptually thick. For instance, if you have two distinct instances of a human class, and both instances have an ID of 2 and the name Johnv, checking them with double equals will return true, assuming the class conforms to the equatable protocol. They hold the exact structural data. Now, contrast that with the triple equals operator, which checks for reference identity. This operator asks, are these two variables pointing to the exact spot in the heap memory? Going back to our two human objects. Even though their properties are identical, they were initialized separately. That means they live at completely different memory addresses. So, if you compare them using triple equals, it will return false because they are separate instances. It will only return true if you point one variable directly to the other, like writing let human2 equals human1. Let's look at the code example on the screen to make this crystal clear. We have a simple human class with an ID and a name. Notice that we make it conform to the equatable protocol so we can define what the double equals operator actually checks. In this case, we're telling Swift that two human objects are equal if they share the exact ID. Now look at how we instantiate them. We create human1 and human2. Both have an ID of 2 and the name Janvi. When we run human1 double equals human2, it returns true. This checks for structural equality. They hold the exact structural data according to our logic. However, if we run human1 triple equals human2, it returns false. This is checking for reference identity. Even though their internal properties match perfectly, they were initialized as two separate instances. That means they point to completely different areas in the heap memory. The triple equals operator will only return true if both variables point to the exact allocated memory block. For example, if you wrote let human3 equals human1. So, remember this rule of thumb for your interview. Double equals checks if two things have the same value, while triple equals checks if two things are the exact instance in memory. Moving on to question number 7. What are some of the key differences between Swift and Objective-C? If you are interviewing for an iOS role, understanding the evolution from Apple's legacy language to its modern successor is highly critical. Let's break down the major shifts across a few key parameters. First, look at the programming paradigm. Objective-C is strictly a traditional, class-based object-oriented language. Swift, on the other hand, is multi-paradigm, blending object-oriented patterns with powerful functional programming capabilities like map, filter, and first-class closures. Second, let's talk about dynamic libraries. Swift fully supports them. This is a massive performance win because it allows applications to link to system libraries dynamically. When Apple updates iOS or macOS, your app can inherit those system improvements automatically without you having to resubmit a new build to the App Store. Objective-C historically relied on static linking. Third, Swift introduces modern data structures like tuples. This lets us group multiple values together quickly, allowing functions to return multiple values without needing to wrap them in a custom class or struct. Objective-C simply doesn't support this. Fourth, from a syntax perspective, Swift completely drops the mandatory use of semicolons, which removes code clutter. In Objective-C, missing a semicolon means a broken build. Finally, consider method definitions. In Objective-C, you can only define methods inside classes. Swift changes the game by letting you write methods, extensions, and protocol conformances inside classes, structures, and enumerations alike, making value-type programming incredibly robust. Highlighting these points shows the interviewer that you appreciate why Apple made the shift to Swift, and how it modernizes the entire development workflow. Moving on to question number 8. What are 3 ways to append 2 arrays together in Swift? This is a practical, code-focused question that interviewers use to see if you understand basic collection manipulations and mutability. Let's look at our setup code first. We have first array declared with var, making it mutable, and second array declared with let. Remember to mention to your interviewer that for any in-place addition, the destination array must be declared as a variable, not a constant. Here are the 3 common approaches. The first approach is using the built-in append contents of method. This is the standard API way to take the entire collection of the second array and copy its elements directly into the end of the first array in place. The second approach is a cleaner syntax shortcut using the plus equals assignment operator. This achieves the exact underlying performance and result as append contents of. It mutates the first array directly by appending the second collection to it. The third approach is used when you don't want to modify your original arrays. By using the plus operator, Swift combines the 2 arrays together and returns a brand new collection, which we can store inside a third array. This keeps both first array and second array completely untouched. Knowing these 3 options shows the interviewer you understand how to balance clean syntax with safe state management in your code. Moving on to question number 9. What are the execution states of an iOS application lifecycle? This is an absolute favorite for interviewers testing senior or intermediate developers because managing app states correctly is vital for battery life, memory efficiency, and a seamless user experience. Let's walk through the 5 distinct states of an app's lifecycle. First, we have the not running state. This is the baseline. It means the app hasn't been launched yet, or it was manually swiped away by the user, or even purged entirely by the operating system due to low memory. Second is the inactive state. This is primarily a transitional state. The app is technically in the foreground, but it is not receiving any UI events. This happens during standard state transitions, like when an app is launching or moving to the background, but it also triggers during sudden interruptions, like when the user receives a phone call, pulls down the notification center, or activates Siri. Third is the active state. This is the main execution state. The app is fully in the foreground, the UI is completely accessible, and it's actively processing user inputs and executing code. Fourth is the background state. The moment a user minimizes the app, it hits the background. In this state, the app can still execute code, but only for a limited grace period, historically around 180 seconds, to let you finish ongoing tasks. If you need more time, you have to explicitly ask the OS using APIs like begin background task. Finally, we have the suspended state. Once that background grace period ends, the OS freezes the app. It stays cached in the device's RAM so it can relaunch instantly, but it is forbidden from executing code, meaning it consumes 0 CPU and 0 battery. However, keep in mind, if another app needs memory and the device runs low, the OS will silently kill suspended apps to free up space. Explaining this lifecycle cleanly demonstrates that you know how to build apps that respect the device's hardware limitations. And finally, let's wrap up with question number 10. What types of objects are considered basic data types in Swift? While this sounds like a beginner question, an interviewer is looking to see if you can categorize them logically and mention the architectural differences under the hood. You can break these down into 3 core groups. First, we have our numeric types. 4 whole numbers. Swift gives us int for standard signed integers and uint for unsigned, positive-only integers. 4 fractional numbers. Swift gives us float for 32-bit numbers and double for 64-bit numbers. It's always good to mention to your interviewer that Swift defaults to double for any decimal number because of its superior precision. Second, we have textual and Boolean types. We have string for text manipulation, character for single-character literals, and bool for standard true or false flag logic. Third, make sure to include the basic collection types, which are natively treated as foundational types in Swift. This includes array for storing ordered lists of the data type, and dictionary for storing unordered key-value pairs. A great bonus point to throw in at the end of this answer is that unlike many other programming languages where basic types are primitives, all basic data types in Swift are actually structured as value types, structs. This means they are inherently thread-safe and passed by value, showcasing the modern safety architecture of Swift. And that brings us to the end of our 10 essential Swift interview questions. And that wraps up our top 10 Swift interview questions. Thank you so much for watching. I hope these breakdowns help you clear your next technical round with absolute confidence. If you have any feedback or if you noticed a correction needed on any of the slides, please let me know in the comments below so we can keep this guide accurate for everyone. Don't forget to like, subscribe, and share this with your fellow iOS devs. Good luck with your interviews, and I'll see you in the next one.